Hi everyone, my name is Eloisa, and today I'll be talking about epidemics and all the things that we can do in Python to actually gain insight into how they work and how to stop them. So firstly, a little bit about me. I'm Eloisa, I'm a mathematical modeler at the Burnett Institute, and in my day-to-day, I make simulations of infectious diseases, among other things. So the main goal of this work is to project the future evolution that infectious diseases can have, including when they reach epidemic and pandemic levels. And also then to mitigate the impact that they can have on public health. So basically to avert the worst consequences of infectious diseases. I'm also a contributor to Atomica, Cyrus, and StarSim. They're all open source scientific packages. But today I'll be talking mainly about Atomica. I also like hugging goats, apparently, because honestly, who doesn't? So first, I want to give a bit of context about infectious diseases. A lot of people don't know this, but they're actually the third biggest killer worldwide. So if you consider all causes of death in the world, including car crashes and cancer, infectious diseases come at number 3. They kill more than 13 million people every year, and that accounted for 14% of deaths in 2019. This number has only increased, of course, since the onset of COVID. So there are many public health interventions available to us in order to stop epidemics and pandemics. This includes vaccines, testing, and treatment. However, the best approach as to how to stop an infectious disease from spreading is not always clear, because there are many complex factors at play, and it's also very context dependent. So something that works in India may not work in Cambodia or in the UK. There's also very limited funding, so it needs to be spent very strategically so that the funding that we do have has the maximum impact on health. This is why mathematical modeling tools are really useful for this. So we can use them to simulate outbreaks and then the interventions that we would put in place to stop those outbreaks from spreading further. This allows us to determine the most effective approach without actually having to try them out in the real world with real consequences. The problem, however, is that it's actually quite difficult to create epidemic models that are fit for purpose from scratch. So as I said, it's very context dependent, and the different models that we create need to take into account things like which populations are significantly more at risk, or details about the geographical location that we're modeling. So there is a lot of work that goes into that. And of course, after we've established that, a lot of modeling work that goes into creating that from the bottom up. So how can we make this easier for people? Well, this is where Atomica comes in. Atomica is an open source simulation engine that is used for running mathematical models. It's used for many applications, including infectious diseases, maternal and child health, and also sustainability interventions. But there are many more that I don't have time to go into today. I think one of the good things about Atomica is that while it's really easy to use, it's also very highly configurable. It has lots of inbuilt functionality for different things, and because they're kind of structured in sort of different modules, you can pick and choose which ones work for you, which ones are useful to you, and which ones maybe you don't need at the moment. So this includes, of course, the basic functionality of building a model and running the simulation, but also plotting functionality, fitting model parameters to the data, implementing different types of public health programs, and finally, budget optimization. So once we have those programs, how do we allocate funding to the different public health programs in the optimal way? And also, Atomica is developed by people who usually use Atomica on a daily basis. And I think this really creates a sort of feedback loop of improvement, because if you use Atomica every day to make models, if you've made several models, maybe eventually you realize, oh, there's a part of the process that maybe is a bit tedious, takes a lot of time, or maybe it could be made easier by just having that incorporated into the framework, and then not only will it be easier for us next time we build a model, but it can be easier for whoever else is using the package in the public. So now let's look at a hypothetical disease, snakepox. So we've had chickenpox, monkeypox, and now there's snakepox. Don't worry, it's completely hypothetical. I don't want to scare anyone. But let's consider that this disease maybe has been around for a few years, and maybe it's been eradicated in most of the world, but there are still some pockets of very high prevalence, very high infections in certain parts of the world. And now there's a new vaccine, and say the government from one of the areas with very high prevalence has contacted us and they want us to model the impact that this vaccine could have. So they're kind of trying to figure out whether it would be worth it for them to do a vaccine program in their country. So the first thing we need to do is have an idea of the structure of this disease, like how the disease dynamics work. And the way that we do that is with a compartmental model. So compartmental models, the basis of them is they have compartments, which represent amounts of people, and these are the green rectangles here. And then we have flows, which are the orange arrows, and they represent amounts of people that flow from one compartment to the next. Here we have an example of a simple disease model, which is SIR. It's basically the simplest compartmental model that we could come up with for epidemics. And it stands for, of course, susceptible, infected, and recovered. So people start off in susceptible, they flow into infected at a rate mediated by the infection rate, and then they go from infected to recovered at the recovery rate. So I'm going to add a little bit more detail just to make it slightly more realistic. So I'm going to add births and deaths. So that means we have the extra parameters of the birth rate, and then the death rate due to other causes, and also the death rate due to infection. So what now? We've got our conceptual model. So how do we go from this to having a working simulation? Well, I'll take you through the basic Atomica modeling process just so that we can see the basic steps. So firstly, we're going to make a framework and data book, which are Excel spreadsheets with firstly this conceptual structure that we just looked at, and then the data corresponding to all of those parameters. Then we're going to import those into Atomica and run a simulation, and we're going to obtain some preliminary results. However, that's not usable yet. First, we need to do some model fitting to make sure that our parameters are right and that they work with each other. And then we'll get a status quo scenario. So this is essentially what is likely to happen in the future if we keep doing things the same way we've been doing them, if we don't change the funding allocations or funding level, and we don't put in any new interventions. And finally, we can change things a little bit. So what would happen if we had new public health interventions, a new vaccine, a new treatment, or if we even did the same type of treatment but differently to different populations? So all of these options, we can simulate them, and then that will lead us to alternate scenarios, which we can then compare to the status quo scenario to see which would be better. So let's dive in. Firstly, of course, we've got the model framework, so we're basically converting this conceptual structure into Excel format so that it's easily interpretable by Python. And this Excel spreadsheet has three main pages. Firstly, there are the compartments, which we're just going to list all of the compartments that exist in our model. Then transitions, which are the flows. We're basically saying where those flows are, like between which compartments and which direction they flow in. So they will always go from rows to columns. So in this case, we have a flow from the births to susceptible, another flow from susceptible to infected, and so on. And finally, we have the parameters. So here we're going to state where we can find the values for each of these parameters. In most cases, these will be found in the data book on the flows page, but there's one that we are going to define here, which is the infection rate. So this is going to be a function of susceptible, infected, recovered, and the infectiousness. And I'm going to also add a couple of more parameters. So this is the same spreadsheet, but I'm just making it a bit bigger so it's visible. I'm going to add two parameters that are not part of this flow chart. So they're not flows, but they're just parameters that I want to keep track of in the model so that I can plot them later. So these are the incidence, which is the number of new infections, and the disease deaths, which is the component of the flow from infected to deaths that is due to disease. And now we can fill in the data book. So this is just going to contain all of our data values, which are mostly going to be estimates for our model parameters, including compartment sizes and flow rates. So firstly, there's the stocks page, and this is just filling in the data, so I'm not going to focus on it too much. But essentially, we have also the alive parameter, which is just all of the people alive in the simulation. So all of the people in susceptible plus infected plus recovered. So in 2015, when our simulation starts, we have 1,500 people alive, 1,000 of those are in susceptible, 500 in infected, which means we're going to have 0 people recovered at the initial time step. And then this is just the data for all of the rest of the parameters. I'm not going to dwell on it too much, but essentially we can set them to a constant value. For example, the birth rate is a constant value of 200 people per year, or we can also have a time series. In this case, because it's a very simple example, I've only put 2 data values per time series, so one in 2015, 10 years ago, and one in 2025. But if we wanted to, we could do all the years in between. We could even do data going back to 1970. So it's whatever data you have, you can just put it in here in whichever format works better for you. And now we're ready to run the simulation. So how are the compartment sizes computed? I just want to look at this quickly so that we see what's going under the hood before we actually run the simulation with the code. So essentially at t equals 0, at the initial time point, to initialize the model, it's just going to match the initial compartment sizes exactly, because we need a starting point for everything, right? So it's just going to take those initial data points exactly for the compartment sizes, but then for the subsequent time steps, the model is going to use the flow rates to compute the change in the number of people in each compartment at each time step. So it's just going to use these functions and rates to integrate those changes. And now let's run the simulation. So firstly, of course, we need to import Atomica. Then we're going to load in the framework and data book. So this is going to be just those 2 files that we just created, and we're going to load them into a Atomica project object. So this is just an object that holds all of the information relating to our model, just so that it's all in one place. And then we use the runSim method of the project object to run a simulation. And I'm going to give it a result name of preliminary results. As you can see, it runs really quickly. This is not always the case, but thankfully this is a very simple model. And in case you're interested, this is the code I use to generate the plots. So this is the inbuilt plotting function. So first we create a plot data object with the result and the project in the arguments. And then we'll have essentially our simulation. And using the plot series function, we can put in the simulation and data to signal to Atomica that we want to plot both the simulation and the data that's associated with it. And this is what that looks like. So Atomica has helpfully plotted our 3 main compartments: susceptible, infected, and recovered. And I don't know if you can see this very well, but the initial data points, just kind of on the y-axis, they match exactly. That's because of the process that I mentioned at the beginning, where it matches those exactly. But then later on, the simulation really isn't matching the data at all. Why is that? Well, as I said, a lot of the parameters are just approximations. So it's quite normal that initially the simulation is not going to match the data very well at all. That's why we need to change our parameters a little bit, because often they also come from different data sources. They might not be really consistent with each other. So that's why we need to do this process of model fitting. So model fitting, which is also called calibration, simply consists of fitting all of our simulation parameters to the data. And the reason this is really important is because we need our model to be able to reproduce historical patterns that we've observed in the real world, to be able to claim that it's going to reproduce any patterns that might happen in the future. We can do this manually by going into the data book and manually changing the parameters, running the simulation, seeing how much it's changed, going back to the data book, editing that again. But that is a really long process, and it can be quite tedious. So instead of doing that, we're going to do automatic calibration. Thankfully, Atomica has inbuilt support for calibration. So all we need to do is specify which parameters to adjust, which are going to be the adjustables, and which simulation outputs we want to match to the data, the measurables. And we always do this in a particular order. So here I've put the parameters to adjust, parameters, the outputs that we want to match. And we start with the population parameters, like birth rate and death rate. Then the disease parameters, like the infection rate and recovery rate. And finally, the disease deaths. So why do we do it in this order? Well, that's because we want to start off with the parameters that have the largest overall impact on the total numbers in the model. Because if we started by calibrating the death rate due to infection to perfectly match the number of disease deaths, and then we change the birth rate, we're going to have a lot more people in the population, which is going to lead to more infections, which is going to lead to more disease deaths. So then this parameter that we'd calibrated is now completely uncalibrated again because we've changed these other things. So that's why we do it in this order. And these are just the code names for all of these parameters that we're going to use in the code. And in the code, the first thing we're going to do is we're going to make a new parameter set. So we've got a variable of the project called a parameter set, which is just a copy of all of our parameters. So this is just so that we don't modify the original copy. We're still going to have an original copy, but we're editing our own copy. And these 3 lines of code are essentially this table translated into code. So firstly, we're calibrating the population, then the disease, and then the disease deaths using the calibrate method of the project. And then we just run the simulation. And this is what that looks like. So as you can see, now the simulation results do match the data. So the calibration was successful. And this is essentially a simulation of the status quo. This is what would happen in the future if we don't change anything, if we keep doing things the same way we've been doing them so far, with the same public health programs, the same funding levels. This is what would happen. Essentially, the number of people infected would keep increasing. So now we can look at an alternate scenario. As I mentioned, Atomica has integrated support for public health programs and funding allocation optimization. So the main public health types of programs that I mentioned are testing, treatment, and vaccines. But of course, there are different ways of doing that, different types of treatment, different types of tests. So we actually have a long list of public health programs which we can then plug into the optimization algorithm so that it can then tell us the optimal allocations. However, it would take a bit too long to cover that. So I'm just going to look at what public health programs really do is they affect the outcomes in the model and the outcomes of an epidemic by modifying our model parameters. So we're going to take a little bit of a shortcut by just going in and modifying the data book in a similar way to what a public health program would do. So we're essentially doing the same thing, but without having to go through the whole process of implementing a new public health program. So as I mentioned, we have this new vaccine. And let's say that the vaccine, maybe it doesn't stop you from getting the disease, maybe it doesn't even decrease the death rate, maybe it doesn't even decrease the infectiousness, but maybe it could increase the recovery rate. So if you're vaccinated, you just recover quicker. So in the data book, we have the recovery rate at 0.3 currently in 2025. So if we roll out the vaccine now, say the vaccine doubles the recovery rate, so in 2026, we would have a recovery rate of 0.6. And if we run a simulation of that, these are the results. So you can see the change between the status quo and the vaccine intervention. Rather than having the number of people infected steadily increasing, we're actually managing not to only stabilize infections, but actually decrease them and decrease the trend overall. we've also, of course, got many more people who have recovered from the disease, and actually more people who are susceptible, so more people who never even get the disease at all. This is maybe counterintuitive because we haven't directly changed the number of people infected, we haven't directly changed the infectiousness of the disease, but this is simply because if we have people who are infected for half the amount of time, it also means they have half the amount of time to infect others. So that's why many more people just never end up getting the disease at all. And I also wanted to look at the number of new infections and number of deaths due to the disease. So on the left, we've got the status quo, and on the right, we've got our alternate scenario with the vaccine. And as you can see, both the new infections and number of deaths have decreased thanks to this vaccine. In particular, new infections decreased by 27%, and disease deaths decreased by 34%. This means that we saved 1,075 lives. So I just want to make a quick note. This isn't meant to be a magical crystal ball that's going to tell us exactly what's going to happen in the future. That is not the intention. The intention is more to give us a bit of insight into the disease dynamics and what kind of patterns are likely to play out in the future under different scenarios. So now I want to look at some real-world applications of this work and of Atomica. So recently, my team and I have used Atomica for research on obviously infectious diseases, such as COVID-19, of course, tuberculosis, typhoid, hepatitis C, and others. We've also used it for maternal and neonatal health. So this is a project that I'm on right now, which I find really interesting. I'm basically looking at pregnancy complications, how things like inadequate nutrition can cause those complications and can even cause issues for the baby, and how those issues can even lead to problems into adulthood. So it's very important to address those issues as they're easily fixable, but they still remain a big problem in many parts of the world. There's also another project that I worked on recently on sustainability interventions in a hospital. So this hospital reached out to us saying that they wanted to be more sustainable and put in a bunch of changes, and they had some suggestions such as small things like changing all the light bulbs to more sustainable light bulbs, or doing a training course for all staff on how to recycle medical materials. And we looked at all of these interventions, looked at their equivalent in terms of CO2, and then put all of these into Atomica, and Atomica's optimization algorithm was able to tell us which funding allocations to use, how much funding to put into each program to get the maximum impact from these changes. And of course, many, many more, which I won't have the chance to go into today. But this research, specifically in terms of infectious diseases, is used by governments all over the world to inform public health policy decisions, and also by global health organizations such as the World Bank and the Global Fund to use in their programs. So I want to look at this case study quickly about tuberculosis in Belarus. From left to right, we've got here plots of the number of tuberculosis deaths, number of new active tuberculosis infections, and finally, the number of people with drug-resistant tuberculosis. Drug-resistant tuberculosis is actually a huge issue in Belarus. I think it's the #1 country in the world with drug-resistant tuberculosis as of the publication of this study. And here we can see a comparison between the current conditions, so this is the status quo if we don't change anything, and in red we have the optimized budget. So what I find really interesting about this is that we actually have the same funding level. We are just using that funding in a much more effective way. So just by using Atomica to reallocate where we're spending the money and which interventions we're prioritizing, we actually managed to halve the number of active tuberculosis infections and halve the number of deaths. I think this really speaks to the power of Atomica and these kinds of modeling tools and the impact that they can have on the world if they are widely used to inform public health policy and basically the amount of lives that they can save. So hopefully, I hope the takeaway today will be, on one hand, that Atomica is a really useful Python package. It's a really useful tool for simulating not only infectious diseases, but also a wide variety of other things, both diseases and otherwise, and that when used in public health to tackle the spread of infectious diseases, they can have a big public health impact and save many lives. If you're interested in learning more, please feel free to check out the Atomica GitHub. It's obviously open source, so you can clone it on your machine, edit it, add anything you like. And there are also very in-depth tutorials that go, of course, more in-depth than I was able to in 25 minutes. And one of the things that are covered in the tutorials are things like how to deal with multiple populations, which I didn't have time to talk about today. I've also linked at the end, I'll show you in a second, there's a QR code with links to several different Atomica reports and studies, and also the Jupyter Notebook that I use to run this model and make the plots. So feel free to scan the QR code if you're interested. If you'd like to connect, feel free to connect with me on GitHub and LinkedIn. And again, thank you very much for being here.
Thanks a lot, Eloisa, for that session. So it's time for the questions. Please feel free to ask your questions. Do you have questions? Yes.
Thank you very much. That was a wonderful overview of Atomica. I just wanted to ask, does Atomica have any geospatial support built into it?
Good question. It doesn't really have, any kind of geographical component, but we do often do things where we're modeling different regions separately. So we can build a model for one country or one region and then the neighboring country, or even certain regions of the world. So for example, with the maternal and child health, right now we're modeling some specific countries with very high prevalence, like Nigeria, but then we're also modeling certain regions. So for example, we could model sub-Saharan Africa separately from North Africa, for example, as they have different levels of prevalence. So we don't directly have geography included, but we can make separate models to get a bit of an overview of what the dynamics look like in different parts of the world.
Thank you.
Thank you for the talk. It was very interesting. Yes. I was curious because you saw a scenario of vaccines and trying to mitigate this scenario of the disease, but maybe I miss it. Could you do the opposite case, like play with the malignancy of the virus or the disease or the spreading capacity of it?
So do you mean change how potent the virus is?
Yeah, maybe taking into account the mutations, hypothetical mutations of the virus that could affect the spreading of this disease. So you can take into account this parameter to run the simulations?
Yeah, definitely. So for example, as we know recently with COVID, there were different mutations and they had different levels of spread, for example, or the number of people that they would infect. So that's definitely something that we can do just by changing the parameters in the model. We can even have, we can model that in different ways, but we could model it with different strains, for example, that have different, say, infectiousness parameters. And then we can put those together in the model and see which people are infected by each strain.
So interesting. Thank you.
Thanks.
One last question. Okay, welcome.
Thank you very much for the talk. It's very interesting. I'm wondering what underlying methods used to solve the differential equations that I guess that we're configuring in that CSV file. Is it like an explicit Euler or something a bit more fancy?
Yes, so it does use Euler's method to integrate the ODEs.
Right, okay. And there's no configurability for any other methods?
There is a degree of configurability, I'm certain, for the calibration. So the calibration also uses an optimization function, but for the integration, I'm not sure if you could change which method it uses. But a lot of this stuff in Atomica is quite configurable from what I've seen in the code. So I'm not 100% certain, but I wouldn't be surprised if you could configure your own method if you had a preference.
Cool, thank you.
Thanks.
So we have reached the end of our sessions. In case you have more questions, please feel free to approach the speaker. And also, you can also post on Discord channel if you have more questions. Thanks a lot for the amazing session, Eloisa. We hope to see you again.
Thanks, everyone.
Enjoy your lunch, everyone.